Deeper understanding, broader application, and knowledge in mechanics co-enhanced. 2024 review on generative AI for engineering design of Xinjing Lu's group. Since we first achieved the use of generative AI to arrange shear walls in early 2019, 4 to 5 years have passed in the blink of an eye. This research has gradually transitioned from academic papers to practical engineering applications. At the same time, as our research has progressed, our understanding of intelligent design has continued to evolve. We summarize that 2024 has seen advancements in both deeper understanding and broader application. Deeper understanding of generative AI. In 2023, we essentially completed the 3 engines of generative algorithms: generative adversarial networks, GNs, graph neural networks, GNNs, and diffusion models, along with the 4-stage design process of vertical component layout, horizontal component layout, component dimensioning, material consumption evaluation, which has now entered the stage of practical application. In 2024, we revisited and critically examined potential issues in our previously proposed technical roadmap and began exploring better solutions. Some key achievements include 1. Representation of drawing information. Initially, we used different colors to represent various design information on drawings, such as gray for partition walls, green for windows, and blue for doors. However, as our research deepened, we realized that this color-based representation of drawing information did not align well with the needs of computational feature extraction. To address this, we proposed using n-dimensional masks to represent different design information. This approach overcomes the interference caused by the erroneous prior knowledge inherent in carbon-based vision, color-based representation, and fully leverages the strength of silicon-based vision in handling high-dimensional information. With this simple adjustment, we significantly improved the design performance of both GNs and diffusion models. 2. Fusion of text and image data. To enable textual information, for example, seismic intensity, to guide structural generation, we initially employed a method of expanding the dimensions of both text and image data and then combining them using the Hadamard product. While this approach allowed the learning of textual features, it reduced the density of information, negatively impacting design quality. Inspired by the concept of n-dimensional masks, we translated textual information into feature masks as well. This allowed for a more efficient representation of textual data, significantly improving the integration of text and image information in the design process. 3. Prediction of mechanical responses. Our initial approach to predicting mechanical responses was an end-to-end method, where a neural network was trained to directly predict mechanical responses based on structural design drawings. However, this method had several limitations. A. It was generally better suited for predicting a single mechanical response, for example, maximum inter-story drift ratio, but performed poorly when multiple values needed to be predicted. B. The neural network had to simultaneously fit both the variation patterns of structural mechanical properties and the variation patterns of loads, which reduced the accuracy of mechanical response predictions. To address these issues, we adopted a physics plus data hybrid approach for predicting mechanical responses. In this method, the AI only needs to fit the parameters of a simplified model, for example, an MDOF model, which significantly reduced prediction errors. This approach also allowed us to obtain the displacement, velocity, and acceleration distributions of the entire structure. 4. Integration of vertical and horizontal component layouts. In our earlier research, we studied the layout of vertical components first, followed by the layout of horizontal components. However, in practical engineering, these 2 tasks are performed simultaneously. Sequentially arranging vertical and horizontal components can lead to poor coordination between the 2, resulting in suboptimal design outcomes. To address this, we integrated the layout methods for vertical and horizontal components, enabling simultaneous arrangement and further improving the effectiveness of component layouts. 5. Component dimension prediction considering load distribution and internal force transmission paths. Previously, we developed intelligent design methods for determining the dimensions of components, such as shear walls and frame columns, using image-based representations and design conditions as the basis for learning. However, as our research progressed, we discovered that component dimensioning is closely related to the distribution of loads and the internal force transmission paths within the structure. The image-based methods we previously used did not adequately account for these factors. To address this, we proposed a heterogeneous graph neural network-based method for component dimension prediction. This approach better incorporates the effects of load distribution and internal force transmission paths, resulting in more accurate and practical component dimensioning. Broader application of generative AI. What encourages us most about applying generative AI to engineering design is this. If AI can learn to generate a realistic photo of people, there's no reason why it can't learn to generate a realistic design drawing. Furthermore, if AI can generate a convincing design drawing for a sheer wall residential structure, why can't it generate design drawings for other disciplines or industries? Following this line of thought, we have explored the application of generative AI in multiple fields, including existing buildings, equipment, and infrastructure design. 1. BRB strengthening design for concrete frames. This year, we collaborated with the China Electronics Engineering Design Institute to explore the use of generative AI in the BRB, buckling restraint brace, strengthening design of frame structures. By learning from architects' drawings, AI mastered the rules for selecting BRB placement locations that meet architectural requirements. This represents a new attempt to extend generative AI from the design of new structures to the strengthening and retrofitting of existing structures. 2. Design of concrete-faced rock-fill dams. Another interesting attempt this year was our collaboration with the China Renewable Energy Engineering Institute to apply generative AI to the design of concrete-faced rock-fill dams. Infrastructure alongside buildings is a critical area in engineering construction. Generative AI has shown significant potential in these domains as well. 3. Fire sprinkler system design. MEP design is also a crucial aspect of building design. This year, we collaborated with the Hong Kong Polytechnic University to apply generative AI to the design of fire sprinkler systems in buildings. By learning from architectural drawings and corresponding fire sprinkler design drawings, AI can now provide a fire sprinkler designed for a given architectural drawing. From imitation to knowledge mechanics co-enhanced, generative AI has already achieved successful applications in multiple fields. But what characteristics should generative AI possess for engineering design? We propose that generative AI in engineering design should embody the concept of knowledge mechanics co-enhanced. This means incorporating knowledge and mechanics into generative AI. While generative AI ensures that the design results resemble those of human engineers, the integration of knowledge and mechanics further ensures the compliance and safety of the design outcomes. This approach will drive the better application of generative AI in the field of engineering design. We can only see a short distance ahead, but we can see plenty there that needs to be done. 2025, Happy New Year!